Hello, I am Dr. Tracy Jamison-Hooks, and I wanted to first kind of introduce myself. I've spent 20 years at NASA Goddard Space Flight Center before joining Arizona State University as an associate professor in the School of Earth and Space Exploration. Working with students like you is honestly one of the best parts of what I do. You inspire me daily and constantly shape how I teach and approach research. One of my passions is FPGAs because this is where science and engineering truly merge. It's more than just overlap, it's a complete integration. And out of that, I've developed a concept I call the SHEP specialist, short for Science Hardware Engineering Platform Specialist. A SHEPS is someone who's cross-trained in both science and engineering. These are people who can design systems and capture and process real-world scientific data in real time, and then turn it into something meaningful. That kind of skill is rare, and it's incredibly valuable right now in both academia and industry, especially for high speed and multi-rate digital signal processing. In my classes, I teach students how to speak what I call the love language of FPGAs, how to really understand scientific measurement at its core, how it is captured, how it's processed, and how it's analyzed. Traditionally, becoming this type of expert could take decades and a lot of luck in finding the right mentor. But I'm working to change that. I want to flatten the hierarchy between science and engineering and open up space for all of us to become something more than what the old pathways never allowed. If you're curious, driven, and ready to build things that matter, you're already on the right track. NASA's next flagship mission will be the Habitable Worlds Observatory. Right now, the flagship is the James Webb Space Telescope. You've seen the breathtaking images, but have you ever wondered how those images are processed and downlinked to you here on Earth? Who were the engineers behind this masterpiece? What are their names? If you've worked tirelessly for years, your designs launched into space, your algorithms crystallized on a spacecraft, would you not want your legacy to be remembered? At NASA, I saw many engineers do extraordinary work with little public notice. My own supervisor and mentor, Dr. Damon Bradley, flew the very first 16-channel Polyphase Filterbank on the Soil Moisture Active Passive mission. Although SMAP for short, although SMAP's radar suffered a mishap affecting the active measurement, the polyphase filter algorithm worked flawlessly and captured data for the radiometer, the passive part of the instrument. And he didn't do it alone. His stellar team included my colleagues, Lynn Miles, Dr. Mark Wong, Rafael Garcia, and FPGA radiation engineer Melanie Berg. What I teach my students is you can't design the algorithm and the FPGA without first seeing the measurement. You must understand what you're measuring, how it behaves, and why it matters. That's why in my course, Signal Processing on FPGAs, I push you to immerse yourself, study the measurement, read about it, gaze at a star daily, meditate, do the math deeply, and only then bring it onto the FPGA. And what does the signal encounter first? a deceptively simple tool, a fast Fourier transform. For habitable world to readout system, we use a more advanced version, the Polyphase Filterbank. If you like more background on me, the Habitable Worlds Observatory, these FPGA algorithms being developed for HWO, and the Polyphase Filterbank, check out the videos linked in the description. Here's what you'll be handing in for this project. There are 4 parts, and all of them matter. First, you will build the 1024 channel Polyphase Filterbank in HDL. And that can be in VHDL or System Verilog. That's the core, the signal processing engine that does all the work. For comparison, the SMAP filter bank had only 16 channels. So this is a big step. Second, there's the end item data package. Think of it as the full guide to your design. It includes block diagrams, interface specifications, register maps, and anything someone else would need if they wanted to pick up your work and understand it. Next, you will build a system design report and put everything in a GitHub repository. This repo gives you version control, collaboration, and a place where your code lives. The report explains what you built, why you built it that way, and shows your architecture with visuals, so it makes sense at a systems level. Fourth and finally, you'll create a test bench. This is where you simulate your design to test that it actually functions before you try it out on hardware. It's a safety check and also a way to show the design is reliable. We are first designing a digital spectrometer, and later we will interface the polyphase filter at the front end of the FFT. You'll see this shortly. A digital spectrometer transforms your time domain signal into its frequency components. This is how we can identify life-supporting properties on other planets, directly supporting the mission of the Habitable Worlds Observatory. Now we're going to break this project down step by step in a disciplined way so that no matter your skill level, you can build what I like to call your alien finder. In Module 1, we start with MATLAB. We'll creating a frequency plan to understand where our signals live. In Module 2, we'll move into a Simulink fixed point model, generate HDL from the model, and actually test it on your FPGA board, streaming data over Ethernet or through the internal logic analyzer, the ILA. In Module 3, we'll shift into Vivado, building the spectrometer with FPGA IP on your FPGA board, and again, test it with live data. Finally, in Module 4, we'll design a polyphase filter front end, integrate it back into our Module 3 design, and test a whole system on hardware. By the end, you'll have taken an idea all the way from simulation to real FPGA hardware, step by step, exactly how real space instruments are built. From my experience, the natural tendency of an engineer is to skip steps or to only have finished certain parts because you're eager to get to the fun stuff. but that's a recipe for disaster. I built many designs myself, and honestly, I've forgotten some of them, and I had to move on to other projects. That's why this discipline, step-by-step approach matters so much. If you follow it, you're not just finishing an assignment, you're creating something with a lasting legacy. You'll have a clear, robust paper trail, and that makes you highly valuable in this field. Visually, I'm restating, let me just move this out the way. Okay. Visually, I'm restating our workflow. In our MATLAB frequency plan, I demonstrate how to model your signal for just a single frequency. In all modules, I include my own sine wave generator so you can test your algorithms before interfacing with the outside world. So after the MATLAB frequency plan, you can quickly build a Simulink fixed point model using hardware description language blocks. From there, you can generate HDL code and verify a functional design on your FPGA using internal logic analyzers, ILAs. Next, you replicate the Simulink model, but with equivalent blocks from your FPGA IP library in Vivado. For example, the NCO block in Simulink corresponds to the DDS block in Vivado. The HDL magnitude block in Simulink corresponds to the Cordic in your FPGA library. You then validate this design on hardware. Following that, you build the polyphase filter front end in your own HDL code and integrate it in the front of the FFT. I will provide videos to guide you through all of these steps. You must follow the steps in the videos exactly. Learning by doing is the method I have successfully used to train my students. In the videos, I will rarely speak, letting you focus on observing and implementing. This is another illustration of our disciplined, methodical approach, the same approach that has led to our lab success and our students' high confidence. No matter your skill level, you can achieve these results if you commit to being disciplined and methodical throughout the process. Of course, you must train in MATLAB and Simulink, understand signals and systems theory, and especially be familiar with the fast Fourier transform, the FFT. There are many excellent videos available that can help fill in any gaps in your understanding of FFTs. I like to illustrate my process in multiple ways so that students can begin to see how information resonates with them and develop their own communication skills. If there are any questions, feel free to reach out to me here, and please just subscribe to my channel so I can know that you're out there and appreciate these videos. Bye for now.